Okay, this video is about spontaneity. Now, maybe a better term for spontaneity or spontaneous is going to be favorable or thermodynamically favorable, energetically favorable. Now, you're not going to see that wording on the IB exam, so also not the best term, but it maybe is a better way to think about it because we have a lot of associations with the term spontaneous or spontaneity, which could potentially mislead you in this HL topic. Okay, so what does it actually mean for a chemical reaction to be spontaneous? It means that the reaction is, or the change is self-sustaining without an input of energy. The reaction causes the system to move from a less stable to a more stable overall state, and the reaction releases some kind of usable energy to the surroundings. Okay, so in this video, we're going to recap some of the things that we've talked about in terms of enthalpy change and entropy change, and come up with a way where we can actually think about whether or not a process is likely to be spontaneous or favorable, and also there's a way to calculate whether or not a process is going to be spontaneous or not. Okay, so just a few clarifications first to try to get past some of those misconceptions about the word spontaneity and spontaneous. Spontaneous reactions may still require an input of energy to begin because you still have to overcome the activation energy. So the combustion of methane, for example, we know that methane is natural gas, methane can burn, and once you start burning the methane, it will self-sustain and you'll have a nice flame from that. But you still have to spark the methane in order to get that reaction going. So just because something is called a spontaneous process does not mean that it's going to just happen without any initial input of energy. So I think you hear the term spontaneously combusts, and you think of things bursting into flames, but you actually can have combustion that is technically a spontaneous process, but it doesn't mean that things are just bursting into flames. You still have to get the fire started somehow because you have to supply the necessary energy to overcome the activation energy. We also have reactions like the combustion of diamond, which can happen. You can combust a diamond, and it is technically spontaneous and thermodynamically favorable. But it really never is going to happen under any sort of normal conditions because the activation energy is so high that it won't really take place. So spontaneity does not mean that it will necessarily immediately react when you put the reactants together. You still have to consider sometimes an initial input of energy because of activation energy. Spontaneous also does not necessarily mean fast in this context. Okay, so in our context here, it's going to mean we're moving from less stable to more stable in terms of the overall thermodynamics of the situation, which has to do with potential energy, internal chemical potential energy. That's our enthalpy idea, and also in terms of entropy, the amount of disorder. So things like rusting, for example, rusting is a spontaneous chemical reaction, but it takes hours and days and years for pieces of iron to rust. So it doesn't mean just because rusting is a spontaneous reaction that it's going to happen really quickly. It just means that it's overall energetically favorable and it will likely proceed over time given the right conditions. So this term spontaneity can be, again, it's potentially a bit misleading, which is why I'm kind of going over these common misconceptions about it. Now we also have reactions that can proceed quite quickly. One reaction we haven't seen yet in the redox unit, we'll look at electrolysis, which is using electricity to force chemical reactions. Now those reactions are by definition non-spontaneous. They won't happen unless you put in work to force them to happen, and they create a state that is less stable overall, but they can proceed quite quickly. So you can force non-spontaneous reactions to happen quickly. So again, just avoid thinking of the term spontaneous equaling something about speed. It doesn't necessarily tell you anything about the speed of the reaction. And finally, enthalpy change. Enthalpy change will be one very important consideration when we think about spontaneity, but they are not exactly the same thing. So they're related. We've talked about how when you have a reaction and you've got enthalpy on the left, and you've got the reaction coordinate on the x, that if you go from high enthalpy to lower overall enthalpy, and this is your change in enthalpy, that these products, in this particular example, these products are more stable. And they're more stable because they have less stored energy now. They have less potential energy. Another way to explain it is that they must have stronger bonds, which also makes them more stable. So having exothermic reactions, as I've shown here, when we have an exothermic reaction, it is more likely to be a spontaneous reaction, but that isn't the only factor that we're going to consider when deciding whether or not a given process or reaction is overall spontaneous. We're going to have to consider the enthalpy change, but also the entropy change. So let's go there now. Now, we kind of did this previously. We've already introduced this concept of entropy, this concept of disorder, and we've talked about how basically the second law of thermodynamics says that over time, the universe always increases in entropy. So we always get more disorder. Now, in a given system, so like a given reaction that we might look at or a given change, we might decrease entropy, which means we might make it more ordered. But in doing so, that means that the surroundings must have become more disordered. Overall, the system and the surroundings, the total universe, entropy is always increasing. And we've seen that that's like a probabilistic argument, that it's just more likely that things become more unorganized over time, because to be highly ordered is quite specific and very probabilistically unlikely for things to become more ordered over time. So for entropy change, we use the symbol S or delta S. And so of a system, we can have an increase or a decrease in entropy. So positive delta S means the entropy increases over time, and negative delta S means the entropy decreases over time. So again, we're talking about if it's a positive change, then we have more disorder. Not more order, more disorder. And if it's a negative entropy change, we have less disorder, which is more order. And we talked about things like, especially phases, the state of matter can impact the entropy, and so you're looking for things like, do I have liquid on one side and gas on the other? That would represent a big increase in the amount of disorder, the amount of entropy. Or do I have 1 mole of gas on the left and 3 moles of gas on the right? More particles means more disorder, things like that. So you should be able to look at chemical reactions and changes of state and decide whether or not we are increasing the disorder or decreasing the disorder. And we can also use table 12, and we can actually get a value for what is the delta S of the reaction. You just add up all the entropy values for the products, and then you subtract all the entropy values for the reactants to get a delta S value for the reaction itself. We'll come back to the important consideration here about units, or maybe I'll point it out now. We are going to have an equation that links delta H and delta S to delta G, and that's our final value for the unit. And it's really the most important one when we're talking about spontaneity. You'll notice that delta H and delta G both have units of kilojoules per mole, and S has different units. It has a K in it, that's Kelvin, so it's related. You have to involve temperature here to cancel out that Kelvin unit. But also you'll notice that the unit of energy in the S unit, or the S value, is in joules. And so there's always going to need to be a conversion here to kilojoules. So these values, really, the S values need to be divided by 1,000. If you do that, then you'll have them in kilojoules per Kelvin per mole. And you'll see that those values end up quite small that way, like 1.186 and 0.230. But that's actually how you should work with them when we do calculations with them. Okay. Now, what we've basically seen is that in order for overall a process to be favorable, to be spontaneous, you actually have to consider both enthalpy change and entropy change, and actually also temperature. And we saw this when we talked about some phase changes, right? So I think we talked about freezing and melting in a previous class. And if you think about melting of water, let's just say the melting of water. Okay, the melting of water, if we think about it in terms of delta H, melting is an endothermic process. Heat will be absorbed by the ice, and that will break the hydrogen bonds that are existing between all the water molecules, and so it'll separate them. So this is a positive delta H value. This is endothermic, and endothermic changes are less likely to be favorable because you are absorbing energy and going to a higher potential energy state. So this goes to a higher potential energy state. Okay, but if we look at melting water from an entropy standpoint, we're going from solid to liquid, and solid is the most ordered of the states of matter, and liquid is less ordered because the particles now have freedom to move around. So in terms of the entropy, we would say this is a positive entropy change. We have more disorder in the products than we do in the reactants, or in the liquid than we do in the solid ice. So we've got more disorder, which is favorable. We've got a higher potential energy state, which is not favorable. So this is an example where whether or not this process is spontaneous depends on the temperature. And so when does water melt spontaneously? Well, it will melt spontaneously above 0 degrees Celsius. And so if we have a high enough temperature, then this process becomes favorable or becomes spontaneous. And if we have too low a temperature, then this process won't be spontaneous. And we know that kind of from our everyday experience, that ice will only melt if the temperature is high enough. And so we're going to see that there's an equation that combines these three factors, the delta H, the delta S, and the temperature, and allows us to figure out whether or not a process is spontaneous with an actual calculation. We could then also do this in reverse. We could talk about the freezing of water. And the freezing of water would be, if I do it in a different color, so freezing. So everything will flip, and we'd have a negative delta H, so exothermic, freezing. The water molecules get rid of heat energy to their surroundings. So we're going to a lower potential energy state. That's favorable. We're getting a lot more ordered because we're making a solid ice cube. So this is less disorder. So this is unfavorable. And so anytime that we have a delta H and a delta S term where one is favorable and one is unfavorable, then it's going to be temperature dependent, whether or not it is spontaneous. And so in this one, we know that water only freezes if we have a low enough temperature. And if we have a low enough temp, then freezing will be spontaneous. If we have too high a temp, like above 0, then it won't be spontaneous and it won't happen, okay? So we got to look at our delta H, our delta S, and our T. Now the actual equation is here, and the actual value that will give us a definitive answer on whether or not something is favorable, whether or not something is spontaneous, is called delta G. It is the free energy change, or sometimes called the Gibbs free energy change, which is why it has a G. Gibbs was somebody's name. But often the IB will just refer to it as the free energy change. We can see that this equation does exactly what we were looking at up above. We have the delta H term to consider, we have the delta S term to consider, and we have the temperature term to consider. And the temperature has to be in Kelvin, which means it's always a positive value, because the lowest Kelvin temperature is 0. And we can see that the temperature is being multiplied by the entropy term, and that's why the Kelvin unit will cancel out. And so we'll end up, everything will be energy per moles. Okay, so let's think through the possible scenarios here. Oh, sorry, let me come back here just for a moment. in the end, when we use this equation, if we plug in our values, delta H, temperature in Kelvin, and delta S, where we've converted to, so divide by 1,000, convert it into kilojoules. When we plug all those values in, if we get a negative value for delta G, then we say the reaction or the process is spontaneous. It means it's favorable, and overall it is releasing some kind of useful energy to the surroundings. If we get a value of delta G that is positive, that means it's non-spontaneous, and we have to put in work to make it happen. Okay, so that's going to be how we decide. These are some reminders about units that we've already mentioned, and let's go through the various scenarios. So we just did a couple of scenarios in the previous thing. I was talking about freezing and melting. So when we saw an example like melting, we said the delta H was positive and delta S was also positive. So we had an endothermic reaction and we had more disorder. So we have one thing that's unfavorable and we have another thing that is favorable. And what we saw is that this was sometimes spontaneous, and it depended on the temperature. So anytime that we put a sometimes into this column, that means that it's only sometimes spontaneous and it's temperature dependent. That's what I mean by sometimes. So it's temperature dependent. Okay, and we said that melting will only occur if the temperature is high enough. So at high temperatures, it will be spontaneous. Okay, now that means that delta G here is going to be both positive or negative depending on the temperature. So it'll be spontaneous at high temperatures. That means delta G will be negative at high temps, and it will be positive at low temps. Okay, let's try to connect it to this equation. The delta H term stands alone, and we know that the delta H term in this scenario we said was endo, which is unfavorable. Then we are subtracting some kind of Kelvin temperature, so this is a positive value, and we have delta S is also positive. So in this instance, a positive times a positive, our term, the entropy term over here, the entropy and temperature term, will be overall positive. So I'm subtracting out a positive value. Okay, so what that means is we've got a positive and we're subtracting something from it. When this term on the right gets big enough, then delta G will become negative. But if the term on the right is small, then the delta H positive term will be bigger, and overall delta G will be positive. So that's how the temperature-dependent nature of delta G will actually work out in our equation. Okay, so for example, if this one is 50, just to make up a number, so this was positive 50 kilojoules per mole. At low temperatures, when T is small, then I'll be subtracting out a small number. And so overall, delta G will end up being positive. When T gets large, when it gets very warm, then this will be bigger overall. Eventually, the term on the right will become bigger. And so you'll have 50 here, but this term will become bigger, so you'll be subtracting out a big number from 50, and eventually the delta G will go negative. And so when delta G is positive, we say it's non-spontaneous. And when delta G is negative, then we say it is spontaneous. Okay? And so the temperature affects whether or not this type of reaction is spontaneous or not, and you're multiplying it by that entropy term. Okay, the next example we said was freezing. And freezing was all opposites. So we had negative and we had negative. We had an exothermic reaction, and we had less disorder. And that was another one where it was a sometimes. And this is a sometimes, and this one was a spontaneous at low temp. Right? Again, if we go back up here to this example. Okay, so now we're dealing with like a negative 50 as our enthalpy because we're exothermic. So that's favorable, right? It's negative, and it's going to lead to a negative delta G so long as the term on the right is small enough. And so now in this one, we're subtracting, and then we have a positive temperature in Kelvin. And in this example, we said delta S is negative. So in this one, we are subtracting overall a negative number. So long as which means you're making it more and more positive. So long as this value is small enough on the right-hand side, then overall, the delta H value will be bigger, and we'll end up with a negative delta G, and so that'll be spontaneous. So if we keep temp low, then we'll get a spontaneous overall process. Okay, if we make the temp bigger, if we go to a high temp, then this one becomes larger. We're subtracting a negative, and that will overall make delta G positive, and so it will become non-spontaneous. So these first two examples were ones where sometimes it's spontaneous and sometimes it's not, and it depends on temperature. The actual temperature at which it switches, you can solve for that by setting delta G to 0. And if you set delta G equal to 0 and solve for the temp, that is the temp at which it switches from spontaneous to non-spontaneous. Okay, there are some other scenarios to think through, and this is sort of a common paper 1 question where they're giving you delta H, delta S values and saying, when will this be spontaneous, when will it not be spontaneous? So we have, so far we did positive, positive, and we did negative, negative for delta H and delta S. So let's try where we mix up those two. Well, in this case, so we have, in the first one, endothermic, and we have negative delta S, which means less disorder. So if you plug in a positive value for delta H, and then you subtract a negative delta S value, delta G will always be positive. There's no way to plug in a positive delta H and a negative delta S and have the delta G term come out negative. It just can't mathematically happen. So in both of these terms, the delta H and the delta S are unfavorable. And so this is never going to be spontaneous. Okay, so this is an example. If you have an endothermic reaction that also creates more order, then it will never be a spontaneous process. It doesn't mean that you can't make it happen with enough energy input, but it will never self-sustain, and it will never make a more stable scenario. Now in the next one, if we go down, we think of it's an exothermic reaction, which is favorable. We're releasing chemical energy, becoming more stable from a chemical standpoint. And if we are creating more disorder, so that's favorable from an entropy standpoint, then this kind of process will always be spontaneous, no matter the temperature. That doesn't mean it's going to spontaneously combust, remember. We might still have to spark the reaction. We might have to give it some initial energy to get going. But it should be self-sustaining, and it will always be a favorable process. So these are reactions like combustion reactions. Combustion is a highly favorable, energetically speaking, a highly favorable reaction. Now, there are also ones where we don't really have to consider delta H, and these were those examples about like things mixing. And so when things are mixing and they're becoming more disordered, if there's no energy change involved, then those are always going to be spontaneous. So it's always spontaneous to create more disorder if there's no energy consideration to have, like no delta H term to consider. But if things become more ordered, so negative entropy change, so like organizing something in your room, cleaning your room, that will always be non-spontaneous. So that's never spontaneous. And you're always going to have to put in work to create more order or less disorder. It's like mixing. This is unmixing. Okay? Okay, so that's like an overall table to consider all the possible combinations of delta H and delta S. These first 4 rows, these are, they do give you this on paper 1. They give you different combinations of positive and negative delta H and delta S, and maybe delta G, or maybe they just ask you, which of the following is always spontaneous, which is spontaneous at high temp, which is spontaneous at low temp, and they expect that you can work that out on paper 1 without the equation. In terms of paper 2, then you're actually going to be using this equation, using values of delta H, T and delta S and solving for delta G. Or if you have delta G, you might be solving for one of the other values, including the temperature. And so that's how we actually decide whether or not a process or a change is overall spontaneous or favorable. We have to consider delta H, delta S, and temperature, those three things. And we have to watch out that our temperature values are always in Kelvin and that our delta S values are divided by 1,000 to be in terms of kilojoules. So that was a long video, but I hope it gave a good overview of the different combinations and how we would use this equation.